Well, hello, my little friends. We've got isosceles and equilateral triangles today. Make sure you write your name and your period on your paper. And our question for today is, are all equilateral triangles also considered isosceles triangles? The answer is yes. Explain why or why not. Okay, so let's get to our definitions. Our first definition for today is a isosceles triangle. The definition of an isosceles triangle is a triangle with two congruent sides. So it's a triangle with two congruent sides. Sweet. So let's go ahead and mark two sides on this triangle that I've got there. I've got a side here and a side here. Now it's isosceles. Now every side and every angle has a name in an isosceles triangle. So these two congruent sides, we call them legs. I guess because there's two of them, so legs. I guess we could call them arms, but we call them legs. Now the non-congruent side, this side right here, would be the base. Base. All right, now just because this is on the bottom, that does not mean that's where the base is. If this were spun around, this would still be the base over there, because the base is the one where the two sides aren't congruent. The two congruent sides are always the legs. So if the triangle is drawn this direction, this one would be the base now. So base does not mean bottom of the triangle. Base just means the non-congruent side. All right, the angles have names as well. The angle between the two legs is called the vertex angle. And then the other two angles are called the base angles because, well, they touch the base. All right, so now we get to the Isosceles Triangle Theorem. So the Isosceles Triangle Theorem says that if, we've got two sides are congruent, the Isosceles Triangle Theorem, so here I've got two sides congruent, the Isosceles Triangle Theorem says that the base angles of an isosceles triangle are congruent. So what this means is that this angle and this angle, these would be the base angles because this is base, and then these would be the base angles. So I purposely drew this on its side because we know that base doesn't mean that it's the bottom. Doesn't mean bottom. All right, so if we know that we've got an isosceles triangle, which we do here because these two sides are congruent, then these two base angles right here are going to end up being congruent as well. So let's do a problem with this. All right, so we've got a vertex angle up there. So that's our vertex angle. And these are our base angles. All right, so on this one, we know our vertex angle is 70, and then we know that this angle here is x. Well, since this is a base angle and this is a base angle, these have to be the same, which means this one is also x. And now we can use the Triangle Sum Theorem to solve for x, because the three angles, x plus 70, always add up to 180 degrees in a triangle. So I would get 2x plus 70 equals 180. I'd subtract 70 from both sides and get 2x is equal to 110, and divide by 2 on both sides and get x is equal to 55 degrees. So now I know that x is 55. So if this angle right here is 55 degrees, we can now solve for y. We can say these two are linear pairs. See, they're two angles that are adjacent that are supplementary because they make a straight line. We could just say that this one plus this one equals 180. So we can say x plus y equals 180 because they're supplementary, they're linear pairs, they're adjacent and supplementary. So instead of x, I now know that x is 55, so I can write 55 plus y equals 180. I'll subtract 55 from both sides, and I get y is equal to, I don't know, like 125-ish? Yep, 125. And now I know what y is. I could have also used the exterior angles theorem and said 70 plus 55 equals 125, and that would have been equal to y as well. All right, the converse of the isosceles triangle theorem. The converse of the isosceles triangle theorem says, well, just the opposite of what the isosceles triangle theorem says. It says that if the base angles are congruent, then the legs are congruent. So here we've got two base angles that are congruent. That would make this one and this one legs, and now we would know those would have to be congruent as well. So if these base angles are congruent, then we would know that these two legs are congruent. All right, we're almost there. Well, not really, but let's just play along. All right, definition of an equilateral triangle. So equilateral triangles are triangles with three congruent sides. So an isosceles triangle had two congruent sides, an equilateral triangle has three congruent sides. Now, since these sides are the same, you can actually use the exact same, the isosceles triangle theorem. Gosh. So if these sides are the same, these angles are the same. If these sides are the same, these angles are the same. And if these sides are the same, then these angles are the same. All three of these angles have to be the same. Well, we know they add up to 180, so that means that all of these angles are just 180 divided by 3. So these would all have to be 60 degrees. So using the isosceles triangle theorem, we can also use it for the equilateral theorem. So all of those would have to be the same. And we call that equal angular. Which means that all the angles are congruent. And in the case of a triangle, if all the angles are congruent, that means they have to be 60. Because if they're all the same and they add up to 180, each of these would be 60. Okie doke, here we go. So example 2, I've got a little bit of both going on here. I've got, it looks like on top, all three sides are the same. So this one's an equilateral triangle. And then on the bottom, this triangle down here, looks like it's only isosceles. So I've got an isosceles triangle and an equilateral triangle up there. Well, if this is an equilateral triangle up there, I can now state that all these angles are going to be the same, so they're all 60. They said that angle A is 82, so I'm going to add that down here as part of my given. And I also know by the isosceles triangle theorem, since these two sides are the same, then these base angles down here are the same, which means this angle is 82. So how do I find my last angle over here? Well, I just take 82 and 82, that's 164, and I subtract it from 180. So I would just do 180 minus 164. It looks like 16 degrees for this last angle here. So this one has to be 16 degrees. Now I can answer all the questions. What's the measurement of angle C? Angle C must be 60. What's the measurement of BDA? BDA, that would be the 16 degree angle. What's the measurement of ABC? Let's see, ABC, that would be this whole angle right there, which would be the combination of 60 and 82. So that makes 142. And there's my answer. All right, last problem. Example 3. All right, this one's a bit of a sticky wicket because I've got two overlapping triangles here. But let's look at this. If I hide some of my triangle, so now I can see I've got a triangle over here, and this triangle just so happens to be isosceles. This leg is the same as this leg right here, which means that these are base angles. This is 30 and this is 30 in that triangle. So I can now know that this angle is 30 degrees. All right, let's look at the other triangle. Here's another triangle over here. It again is isosceles because these two are the same, which means that this one has to be a base angle and this one has to be a base angle. So I know that in this big triangle going this way, since these two sides are legs and they're congruent, then these two angles over here have to be congruent. So now I know that this one has to also be 30 degrees. All right, now it's all what you look at. Let's just look at this small triangle here because we got another triangle right there. Well, I've got 30 and 30 right there. That's 60 degrees, which means if I use the Triangle Sum Theorem, that I've only got 120 degrees left for this top angle. And then, using vertical angles, we can now say that this is the same right here. So this would also be 120 because of vertical angles. And then using linear pairs, we could say that this is 60 degrees. So it's all about ignoring pieces of the puzzle so that you're only looking at one triangle at a time. Now I'm looking at only one triangle here, 30, 60, and then Z. Well, 30 plus 60 is 90. If I subtract that from 180, I'm left with 90. So Z must be 90 as well. And now I have everything I needed. X was 30. And we knew that from this triangle right here, because these were isosceles and this was 30, so that angle's 30. So we found that. Y we found out was 120. And we found that out from the triangle in the middle right here. We saw that the two bottom parts were 30. So 30 plus 30 is 60. That leaves 120 degrees for the top angle. And then we use vertical angles to find Y. And then our last one, we just covered up this triangle over here. And so we're just looking at this triangle on top. We had 30. This is 120, so this has to be 60 because those are linear pairs right there. So we got 30 and 60, and then we subtract that from 180. We found out Z has to be 90 degrees. So covering up your triangles as you're working, a lot of times is very helpful when you've got stuff overlapping and there's just a whole jumble of information there. Covering up and looking at one triangle at a time is very helpful. That's all the lesson I got. I'm done. Go do your work. Bye-bye.